Hi, the standard for this video is rationalizing radical expressions. We've got some objectives, include what is a radical expression, rationalizing monomials, rationalizing binomials, and then rationalizing numerators and denominators. So what is a radical expression? We start with a definition. A radical expression is an expression that contains a radical. The radical may be expressed as a rational exponent. So we're using the kind of definition or the word to define itself sort of thing, but we'll do some examples if you don't remember what a radical is. And we can put almost anything here, but square root of x is the first one you learn. We also know that's the same as, or we're refreshing right now, the same as x to the 1/2. So that's that rational exponent, right? Those rational numbers were the ones we could write as fractions. And we can have some bigger expressions in there too. We can have some terms outside the radical. We could have kind of a mix of each. But as long as we've got that rational exponent or a radical somewhere, it's a radical expression. So not a radical expression, really literally anything else, right? We can have some polynomial pieces. We can have just a constant. Those trig functions aren't radicals. Maybe a natural log, that's not a radical. So a lot of other things we could have, but if it has a radical in it, radical expression. So to rationalize a numerator or denominator is a method to rewrite the numerator or denominator without a radical. So in math, we normally see rationalizing denominators when we simplify trigonometric values. We see rationalizing numerators when working with limits in calculus. It could be numerator or denominator, but they'll do numerator a lot. So rationalizing monomials we'll start with. We do this in trig. Note, generally we deal with square roots in trig and calc, so that will be our focus here. And we'll start with a recall for that square root to kind of talk about what we're doing. We have that the square root of x equals x to the 1/2. So the square root of x squared would be the same as x to the 1/2 squared, which if you remember multiplying those exponents together for our exponent rules gives us a 2/2 or just x to the 1st. So when we square a radical or multiply it by itself, we're going to break out the radicand, that value underneath. So to rationalize the denominator here, I think we did the 1/√2 when we were doing some of the trig. We'd have to multiply by 1 in the form of the square root of 2 over square root of 2. We can't just square numerator and denominator. That doesn't give us an equal value. We can only multiply by 1 to keep it the same. But multiplying by √2, or multiplying it by itself, is us squaring that denominator, or squaring the √2. So we do get the radicand out like we showed above. And in the numerator, we get the square root of 2, because times 1 won't change that value. For b, we're multiplying by that square root of 6 that's in the denominator, essentially squaring that value, but multiplying by 1, so we keep the value of the fraction the same. In the denominator, we just get that 6 out. In the numerator, we can't take the 4 underneath the radical, so we get a 4√6. And then we want to simplify where we can. Right, 4 is 2 times 2, 6 is 2 times 3, so we can divide out one of those 2's. And we get a 2√6 over 3. For c, we still have that monomial in the denominator we want to rationalize. So we're going to multiply by itself, right, in order to create that square and break out that radicand. We'll multiply the numerator by the same thing. Remember that we're multiplying fractions, so we're going to have to distribute through every term in that numerator. So the root x times itself, or root x squared, is just going to give us that x. Since they are under the same radical, right, both square roots, we can multiply those factors together underneath. So we get a square root of 2x. And then the root x times itself in the denominator gives us an x, and we are done. Right, we can't divide those x's. The one in the numerator is a term. For rationalizing binomials, which we'll see more in calc, we start with a note. To achieve the desired result with 2 terms, a binomial, we need to multiply by the conjugate. This is true if one or both of the terms is irrational. An irrational we had under those radicals, right? We talked about the number types in that first lesson. So definition here, we have conjugates. Are binomials with the same 2 terms, but opposite signs in between them. So the conjugate of a plus b is a minus b, and vice versa. Recall the product of conjugates results in a difference of squares. This a plus b times a minus b we looked at in that factoring video gives us a squared minus b squared. Right, the ab from the inner terms and the minus ab from the outer terms would go to 0 and leave us just with the a times a and b times minus b, so the a squared minus b squared. And what's important there is, again, if either one of these terms or both are irrational, when we square them, we'll break out that radicand. So we are going to multiply the expression by its conjugate and simplify the result. For a, we've got 2 minus root 3. So we want to multiply by 2 plus the square root of 3, right? That opposite sign gives us our conjugates. And we don't have to do the foiling. We know it's going to be the first term squared minus the second term squared. And squaring is going to either square the value, right? 2 squared is 4, or break that value out of that square root, that radical. So we get a 4 minus 3 here, which is just 1. For b, we want to make sure that this whole radical is our a, or make note of it, right? So it's a minus, this is our b. So when we multiply by our conjugate, we need an a plus b. That becomes a root x plus 1, right? It's important the sign under there doesn't change. That term has to stay the same. And then a plus 2 for our second term. And when we multiply those out, we'll get the square root of x plus 1 squared minus 2 squared. You're welcome to skip that step once you've done it and it makes sense to you. So we're just going to break out that radicand, the expression underneath, and then we've got a minus 4 from the 2 squared, which gives us an x minus 3 when we simplify. All right, so where we'll see it in calc is more part of this not rational expression, because we'd need a polynomial right in that denominator, but we will see it when we have these fractions. And so recall here, in order to manipulate a fraction or rational expression, we need to multiply by units of 1, meaning whatever you multiply to the numerator, you must also multiply to the denominator, since box over itself is 1 for all values such that that box is not 0, right? So whatever value or expression is there, if we divide by itself, we get 1. We did it with single values above. Now we're going to do it with conjugates. So for 3, we're going to rationalize the denominator and simplify the result if possible. In the denominator, we have our radical or irrational expression there. So we want to multiply by the conjugate. Again, that whole radical piece is a single term, right, for the denominator. So the x squared plus 16 is going to stay. And we're going to change that sign in the middle of the 2 terms to a plus 4. And if we multiply to the denominator, we've got to multiply the same thing to the numerator. Right? So we're multiplying by 1, and the value of the expression doesn't change, even though it looks different. The important part for a lot of these is not to try and distribute or multiply out that numerator, or whichever one we're not trying to rationalize. Right, the one that our goal is to rationalize is the one we're going to do that difference of squares with, but the other one we want to leave factored out so we can see if we can simplify further. So we just write it as an x times the whole numerator here, the square root of x squared plus 16 plus 4. Right, so it's x times that whole quantity over, we get, if we skip that step where we write it with the square over it, an x squared plus 16, right? That whole goal, again, by multiplying by the conjugate, was to break that radical, or the radicand, out of that radical. And then the minus 4 times plus 4 gives us a minus 16. So here we can see some like terms in the denominator. Our numerator stays the same, x times the quantity, square root of x squared plus 16, and then that plus 4. All over just an x squared. And then we can simplify one of those x's. We'll divide out. And we're left with, for our final here, the square root of x squared plus 16 plus 4 over x. All right, reminder again, x squared plus 16, we have 2 terms underneath the radical. We cannot go term by term there. We would need the same value squared, and we can't factor that. So we are stuck. For 4, we're going to rationalize the numerator. This is what we'll see more often in calc. and then simplify if possible. So we've got the square root of x plus 2 minus 3 all over 3. We are going to multiply by the conjugate, in this case, an x plus 2 plus 3. And we'll have to do the same thing in the denominator, again to multiply by 1, to keep the value the same, even though it's going to look different. In the numerator, we get that difference of squares, so the x plus 2 under the radical, when we square it, we just get the x plus 2 out, and then minus 3 squared is a minus 9. All over in the denominator, we get the 3 times that whole quantity, square root of x plus 2, with a plus 3 outside it. And then we can simplify those like terms in the numerator. We get an x minus 7 over 3 times our quantity, square root of x plus 2, and then the plus 3. And that's as much as we can do there. We'll have a problem where we have to substitute in. We're evaluating a limit. We don't do that algebraically here, but for now, we're done. We did that rationalizing the numerator, right? There's no radicals left up there. So jump to the ticket, and we'll do some more together.